Right, so let's look at work. So in this video, I expect you to learn about work, energy, and then the law of conservation of energy. Okay, so what is work? So when they say do work, like usually I tell you in class, do work. Uh, when I say do work, what I expect from you here is that you should be turning in your assignments and you should be kind of sitting down and kind of answering questions or copying notes or maybe taking doing a art puzzle video. That's a work in literal sense. In a literal meaning, that's work. But in physics, when we say you're doing work, it is different, right? So for work to be done in physics, a force, right, needs to be kind of, you need to have a force that is acting on an object or causing an object to move towards a certain distance, right? So you have a force acting towards a certain distance, right? Or you have a force or an object that has weight, for example, being moved towards a certain distance. So for example, those that go to work and their work description is just to stand and watch people. In physics, that is not considered work because they are not moving. So remember, you have a weight. So if you are moving your body towards a certain distance, yeah, that is considered work because your weight is considered a force that's being moved towards distance. So in physics, we say that work is defined as a product of force exerted on an object and the distance the object moves, right? So you remember the distance you're moving needs to be in the same direction as the force. So work is done only when the force succeeds in moving the body it acts on. So if you have force acting on a body and that body does not move any distance, then no work is done. So the formula for work is equal to force times distance. So two things enter when work is done. So for work to be done, guess what? You have a force that is being applied. So if you look at this person right here, she's trying to lift the weight, right? She successfully does work because she took the she wo- she took she lifted, right, all this weight towards a certain distance, right? So in this case, work has been done because you have an applied force, right, and she's lifting it upward, and so the weight also lift upward. So work is done in this case. So work done on the barbell is the average force multiplied by the distance through which the barbell is lifted. So work is done in this case. So if you push against a stationary wall for several minutes, you don't do any work. So if this person is, you look at this image, is pushing against the wall, but no work is being done. No work, absolutely no work, right? Yes, no work because the wall does not move, right? Work is only done when a force is applied and causes an object to move. So the quantity of work done is equal to the amount of force times the distance moved in the direction of the force. So work falls into two categories: work done against another force or work done to change the speed of an object. So check this out. Work is done in lifting a barbell. How much work is done in lifting as twice as heavy barbell as the same at the same distance? So you have twice as much work because remember, the person will need to apply twice as much force in order to lift a barbell that has twice the mass of the initial one. Okay, so this is in accord with the formula that says work is equal to force times distance. So twice the force for the same distance means twice the work done on the barbell. So you do not work when pushing a cart if you push the cart twice as far with the same constant speed. When work when then the work you do is twice as much. So if you push the car with more speed, it means you are applying more force, and so the work is going to be as much, twice as much. Now let's look at energy. Every day we talk about energy, right? And oh, you're running, you have energy. Oh, this person is able to sprint so fast, she has energy. When you're playing football, the person that runs a lot without getting as much tired, we say that person has energy. So what then is energy? So in physics we say energy, right, is defined as that which produces changes in matter, right? The effect of energy observed only when it is being transferred from one place to another. We cannot see energy, okay? We can't see, we can only see the effect of energy. When you look at a person, someone that runs very fast, like we look at the Olympic Games, you see the person that sprints, the first person to reach, we say, oh, that person has a lot of energy because we only look at the effect, right? The action, we only look at the action, the result of what energy does, but we cannot see energy, right? Because it is being transferred. We only see it when it's transferred from one thing to the other, right? So remember, both work and energy, they have the same units. Remember, in physics, we don't have naked numbers, we have units. So work and energy are measured in joules. Remember, they're measured in joules. Just like force is measured in Newton, work and energy are both measured in joules. So the formula is capital J. So now let's look at power. What is power? Again, energy is the ability to do work. I'll add that definition here. Energy is the ability to do work. So if you're able to do work, the ability or the capacity to do work is called energy. Now let's look at power. So how fast work is done is called power. Okay? How fast work is done is called power. So let's say you're moving objects from one area to another area, right? And you have two people moving that are trying to transfer, like they're carrying objects from point A to point B. The person that is able to do more work, that is carrying object from point A to point B faster, is considered to have more power than the other one, because power is equal to work done per unit time. So how much work you've done divided by the time interval, right? So if you do it in a shorter time, you have more power. If you do work in a shorter time, you have more power compared to someone that does work in a longer time. Okay, so the unit for power is the joule per second or the watt. So the unit for power is in the honor of another scientist called James Watt, while the unit for energy and work is the joule in honor of a scientist called Joule. Now let's check this out. You have a job, can be done slowly or quickly. Both may require the same amount of work, but different amount of what? Power, right? So if you do work quickly, we say you have more power than someone that does work slowly. So power is the rate at which work is done. Now let's look at different forms of energy, right? Energy, potential energy is one form of energy, right? So the energy of position is what we call potential energy. For example, look at this ball right here. This ball is at a certain height, okay? So you don't look the length of the inclined plane, but you look at the height of the ball. Right? The potential energy of a 10 Newton ball is the same in all cases. If you look at these three cases, the potential energy will be the same because potential energy is the energy due to your height. It doesn't matter the length, it doesn't matter the horizontal height, only the vertical height. The distance from the ground is the only thing that matters. So these three objects, since they have the same mass, they will have the same potential energy because the height in both cases is 3 meters. So potential energy is the energy that objects have because of their height above the ground. So potential energy is defined as stored energy due to position, due to shape or state. It is in its stored state, energy has the potential of doing work. Okay? So the energy of, due to your position, your shape, or your state is what we call potential energy. Okay. Example, drawn ball, stretch rubber band, raised ramp of a pile driver. So now look at what we call gravitational potential energy. When the word gravity is added to potential energy, what comes to your mind? You remember what gravity is? If you don't, pause this video, go back and check what gravity is. All right. The amount of gravitational potential energy possessed by an elevated object is equal to the work done against gravity in raising it. Okay. So remember, how does gravity act? Gravity acts downward. So if you are raising an object up, you are raising an object against gravity. Okay, so the amount of energy that is used to raise an object against gravity or in opposite direction to gravity is what we call gravitational potential energy. Okay, so work done equals force required to move it upward times the vertical distance moved. So work done is equal to force times distance. The upward force when moved at a constant velocity is the weight, okay, of the object. So the work done in lifting it through a certain height, the product is mass times the weight times the height. So that's why we say mgh. So mass times gravitational acceleration times the height. So the formula here, remember, we say potential energy is equal to weight times the height. But what is the weight? The weight is the mass times the gravitational acceleration times the height. So this formula is a formula for potential energy. So the gravitational potential energy examples, if you look at this person here, this person is trying to pull a block through a certain height, right? So pushing it, it is the person is pushing it upward. And so, because it is moving against gravity, that's gravitational potential energy that is actually being applied to do that work. All right. So, check this out. You have a car. Does a car hoisted for repairs in a service station have increased potential energy relative to the floor? Of course. Of course. If the height of an object is changing, especially when it's moving upward, yeah, it will have a change or an increase in potential energy. So basically, when your height is increasing, if you have a different height or a higher height compared to uh, the ground, then you have a higher potential, gravitational potential energy. So now let's look at the work energy theorem. So what does this theorem says? So again, this applies to decreasing speed. So when you're reducing the speed of an object, you bring it to a halt, right? So for example, when you're applying the brakes to slow a moving car, work is done on it, right? The friction force supplied by the brakes times the distance. So when you hit the brakes, you're applying a force on the brakes. So is that brakes, the force applied on the brake times the distance that does work that is used to stop the car. Now let's look at kinetic energy. Kinetic energy here, the energy of moving objects. Okay, this is the energy of moving object. Potential energy was the energy that was stored in object because of their position, their shape, or their state. But here we talk about kinetic energy as the energy of every moving object. And so the formula for kinetic energy is half the mass times the speed squared. Half the mass times the speed squared. So Ke is equal to half mass. The symbol for mass is m, right? The symbol for speed is v. So half mv squared. So if you have a small change in speed, you will have what? If you have small changes in speed, you will have large changes in Ke. Why? Because you're squaring it. Okay, you're squaring whatever you have, it squares it up. Must a car with momentum have kinetic energy? Remember momentum? What is momentum? You remember? We said, if you don't, Pause this video, go back and check what momentum is, and let me know if it has there's a relationship between momentum and kinetic energy. If you thought about it, what you realize is that we said momentum is the inertia of moving objects. Momentum is the inertia of moving objects. So what that means is that if momentum is the inertia of moving objects, then of course, if the object is moving, it must have energy. Okay? So remember, moving objects all have kinetic energy. So the momentum of moving object, yes, due to the motion alone. Okay? So if we come back to the work energy theorem, when work is done on an object to change its kinetic energy, the amount of work done is equal to the change in kinetic energy. Okay? So the equation of the work energy theorem is that the net work is equal to change in kinetic energy. If there is no change in the object's energy, then no work is done on the object. So we have the work energy theorem here. It applies to potential energy also. So if you remember the case of a barbell held stationary, no work is done on it, no further change in energy. Okay. So if you take an object, you lift it up, and then you keep it up, no matter how long you keep it up, no work is being done at that point because position is not changing. Okay. So also the work energy theorem applies to decreasing energy. So the more kinetic energy something has, the more work is required to slow it or stop it. Okay. So consider this. Consider a problem that asks for the distance a fast moving crate slides across a stationary floor in coming to a stop. The most useful equation for solving this problem is, again, work done is equal to change in kinetic energy. Okay. And what is work done? Force times distance. And what is kinetic energy? Half times the mass times the speed squared. So you want to create, or you want to write down an equation that has distance in it, because you are trying to solve for the distance of a fast moving crate that slides across a factory. All right, so let's look at the conservation of energy. If you remember, we talked about the conservation of momentum. So now let's look at the conservation of energy. Kind of the same thing being applied, in the sense that we do not create energy, right? We do not destroy it. It can only be transferred from one state or one object to another. So energy transforms without net loss or net gain in the operation of a pile. Okay, so if you look at this object right here, it doesn't really matter if you're trying to raise an object up, and even if the rope cuts and this object falls, yeah, it's not like energy is lost. Energy will just be transferred. You see, that energy, part of the energy is going to be hit, is going to be transferred to this stem right here. It hits the stem, and what happens? The energy is transferred to it, causing this stem right here to kind of shrink, or to kind of reduce height, because it's being compressed, it's being smashed. Okay. So the work done in braking a moving car to a stop is the force of the tire's friction times the stopping distance. If the initial speed of the car is double, the stopping distance kind of is none of the above right here, because twice the speed means 4 times the kinetic energy. Remember, it's being squared. Okay, you square the speed. So twice the speed means 4 times the kinetic energy and 4 times the stopping distance. So none of that is in our options. All right, so we are going to end here.